Hi students, in the second video for online lecture 12, we are now going to talk about the molecular geometries that have lone pairs. So why do lone pairs matter when dealing with the molecular geometry? It is because they actually occupy space and volume. So as you can see here with our methane example, you have 4 hydrogens attached to the carbon. We would expect those species to have the exact same molecular geometry that we saw in the previous video, which is going to be the tetrahedron. As we can see here, when we go to ammonia, we are still going to have 4 attachments, but those 4 attachments are not equivalent. As you can see in the top here, this is going to be our lone pair of electrons. So our lone pair is going to be occupying our orbital, but it is not going to be bound to anything. This means that it is going to have a bigger volume and create some electron repulsion. When this occurs, we are going to start with the same electron pair arrangement, the tetrahedron, but as you can see, the bound 3 atoms at the bottom do not have that same arrangement. It is going to have a new molecular geometry, which in this case is going to be our trigonal pyramidal. If we were to have 2 lone pairs around our central atom, as you see here in the case of our water, notice that we are going to have even more repulsion. So in this, we need to be very concerned about which central atoms have lone pairs. They are going to change our molecular geometries. So when we are dealing with these molecules, we need to be very careful about how our electrons are going to be interacting with each other. If we were to have lone pair versus lone pair repulsion, this is going to be our worst case scenario. You are going to see that in the case of our water. We have 2 lone pairs that are fighting for open space. This is actually going to cause our bond angle in our molecule to be slightly reduced. Remember that as we are dealing with the tetrahedron, that bond angle should be 109.5, which you will see here for our methane example. But because these 2 pairs of electrons are pushing against each other, notice that our bond angle is going to have been reduced by about 5 degrees. This is an important effect of our electron repulsion. So if we ask for a bond angle and there is a lone pair, we are going to want to at least describe that the bond angle is going to be less than optimal. If we were to have a lone pair and a bonding pair, at least we have one bonding pair that is going to be interacting with another atom, and therefore it is going to have a slightly worse propulsion than what we are dealing with. So in our worst case is lone pair repulsion. Our next best case is lone pair and a bonding pair. And then finally, our bonding pair versus bonding pair repulsion is going to be fairly normal. And we saw that in our last video when we were dealing with the normal rules of engagement for our VSEPR theory. So as you can see here, we are going to get a reduction in bond angle. That is the optimal bond angle for the electron pair arrangement when we are dealing with more lone pairs around the central atom. So let us go ahead and get into our molecular geometries that have central lone pairs. The first one we would like to talk about is going to be from our trigonal planar parent group. So first thing that we're always going to do is look at it based off of electron pair arrangement. Before we had the AB3 group. Well, now what we are going to do is have what we call the AB2E group. The E in this case is going to let you know that instead of having just 3 attachments that are bound atoms, we are now going to have one of those attachments be a lone pair of electrons. So as you can see here, we now have 2 bound atoms. We are now going to have 1 central lone pair. And while the parent is still trigonal planar based off of the electron pair arrangement, we are now going to get the bent molecular geometry. So as you can see here, we are having this pair of electrons go and taking up space. And while we used to have a bond angle of 120 degrees, more than likely, this bond angle that you see here is going to be approximately between 117 and 118 degrees. So it has made the bond narrower because of the electron density you see at the top. So now let us go ahead and go to our next parent family, which was the tetrahedron. That was the AB4 group because we had 4 bound atoms to the central atom. So the first thing we want to do is look at the AB3E group. Well, based off the nomenclature, we are going to have 3 bound atoms to our central atom, and we are going to have 1 lone pair. While this has the tetrahedral parent when it comes to the electron pair arrangement, we are now going to get the trigonal pyramid. Notice that I have a pair of electrons here at the top, and it is pushing our 3 atoms down to almost form what looks like a tripod or that of a trigonal pyramid. So while we had the parent family that had a bond angle of 109.5, you saw on the previous slide, this bond angle here is going to be something about 107 degrees because of the space being taken up by this lone pair and its orbital. What we can also do is now go and remove another atom and make a second lone pair. That is going to be the AB2E2 group. So now we are going to have 2 bound atoms, 2 lone pairs, and while this is tetrahedron by electron pair arrangement to start off with, this is going to be the second version of a bent molecule. So as you can see here, our bent molecule has 2 lone pairs of electrons. That is the highest level of repulsion. So what is going to happen is that we are going to get a bond angle in our water here of about 105. It has reduced this bond angle by almost 4 degrees. So this is a very important thing that I want to make notice. We use the words bent twice, once in the previous example that we saw with the AB3 group, but then also here in our AB2E2 group. The major difference between these 2 bent molecular geometries is the bond angle. When we are dealing with the AB2E group, we had a bond angle of approximately 118 degrees because it was about 2 degrees less from the 120 of the original molecular geometry. But now for this molecular geometry, seeing that our starting bond angle was 105.5, we are going to have a reduction down to about 105. And so while we have the bent name, they actually have 2 different bond angles. You should be very careful in observing that. Let us now go to our expanded valence, and that is the AB5 group. So originally we would have 5 attachments with no central lone pairs, and we would call this the trigonal bipyramidal. But now what we can do is go to the AB4E group. So this means that we are going to have 4 atoms bound to our central atom. We are going to have 1 lone pair. And now you are going to see the importance of this molecule. We start with the trigonal bipyramidal electron pair arrangement, but then we get what is called the distorted tetrahedron, but is actually going by a more important name of the seesaw. The seesaw is the given name or much more universal name for this molecular geometry. There's an important note in here, and that is because of the trigonal bipyramidal having 2 different types of locations, the axial and equatorial. Notice that our lone pair in this case is going into an equatorial position. When dealing with the trigonal bipyramidal, we want our lone pairs to always go in equatorial positions. This is because it is a larger volume with the 120-degree bond angle that we naturally had with the trigonal bipyramidal. And so this allows us to have a easier place to put those species. So in this case, if we have SF4, this would be the seesaw molecular geometry. But now what we can do is go and add another pair of electrons. So let us go to the AB3E2 group. So this means that we are going to have 3 bound atoms, 2 lone pairs on our central atom, and while it's in the trigonal bipyramidal electron pair family, it is now going to be known as T-shaped. T-shaped, as you can see here by where our atoms are located, going here at the vertical as well during the horizontal, can be a little bit of a misnomer in here because you'll still see that there is slight bond angle movement. That bond angle movement is created by these two lone pairs of electrons being repulsed by each other and starting to push these bonds back towards each other. So while they should have bond angles of approximately 90 degrees, that bond angle is going to be something approximately 89 to 88, maybe sometimes 87 degrees if that is the case. As you'll notice here, both of our lone pairs of electrons in our T-shaped molecular geometry are located in the equatorial positions. You will not put your electrons in the axial positions when dealing with this molecular geometry. Finally, we can do one more molecular geometry with our AB5 parent group. This is known as the AB2E3 group. This is the only molecular geometry in which our lone pairs of electrons outnumber the bound atoms to the central atom. So now we are going to have 2 atoms bound to the central atom. We are going to have 3 lone pairs of electrons. While it starts with the trigonal bipyramidal electron pair arrangement, we are now going to go to the linear molecular geometry. How we get these to be linear is that you will notice that the 3 atoms bound to each other are going to form a 180-degree bond angle. This is caused by having 3 lone pairs all in the equatorial positions and pushing against each other. So just imagine having one atom in the top, having a donut or a zone of all electron density around the equatorial positions of the molecule, and then finally having one more atom in the other axial position at the bottom. The bond angle that we are going to get with this is going to be 180 degrees, very similar to that of the basic linear geometry, but it is going to be lone pairs causing this, not just having only 2 attachments. So this is a very, very important molecular geometry and electron pair family because you can see how important electrons are going to be in our different geometries. The final parent that we are going to look for is the AB6 group. This was originally the octahedral family. Let us go ahead and look at the AB5E group. This means that we are going to have 5 bound atoms to our central atom. We are going to have 1 lone pair, and while it starts off as octahedral in the case of our electron pair arrangement, we are now going to get the square pyramid. This means that a pair of electrons is going to take one of the positions. Remember that the octahedron has all equivalent bonding locations. So if we had put the pair of electron here on the left, that is fine, but it will always look like a square pyramid where you will have a base of 4 atoms located as the base of our pyramid, and then all of those going and extending to our vertex here at the top. And as you can see by my drawing here, I have now created a square-based pyramid. The pair of electrons is going to be below the plane of that base. The bond angles in this case, even though we have a pair of electrons trying to push against 4 atoms here, does not do much, and for the most part, the 90-degree bond angle is retained for all of our atoms. The last of our molecular geometries we want to look at is the AB4E2 group. This has 4 atoms bound to the central atom. We are going to have 2 central atom lone pairs, and once again, while it starts as octahedral, do notice that our electrons are 180 degrees away from each other. We do not want to put electrons 90 degrees from each other. So if we have 2 lone pairs, let's get them as far away as possible to reduce our electron-electron repulsion. And when this happens, you will notice that the pairs of electrons are now top and bottom, and we are going to end up getting what is known as the square planar molecular geometry. These four atoms are in a horizontal plane with a pair of electrons above and below the plane. Our bond angle still remains to be 90 degrees between our bound atoms and the central atom, and is very, very predictable for the molecular geometries we've seen. So as you've seen in this case, putting our pairs of electrons in, we want to do the best we can to minimize their repulsion. Now you can see that we have the summary here of the central atoms with our lone pairs. In the previous video, we showed you the basic molecular geometries. Those are the basic 5 that do not have any lone pairs on the central atom. The moment you place lone pairs on the central atom, you are now going to get these advanced molecular geometries. You are expected to know how to get all of these molecular geometries. So how do we predict this? Well, the first thing that we want to do is always draw the Lewis structure for our molecule. This is using the ideas from the previous chapter to at least let us know how many atoms are bound to a central atom, as well as how many lone pairs. The first thing you want to do is count the number of lone pairs on the central atom and the number of atoms bound to the central atom. To get the electron pair arrangement, we are going to consider lone pairs and bound atoms to be equivalent. This means that if I were to have 2 bound atoms and 1 lone pair, you have 3 attachments. This is going to give you the parent family. However, what you will then do is say, once you get the parent, knowing that you have lone pairs on the central atom, then you must go and use your Vesper theory to predict the molecular geometries. So there's a very nice progression when working through our molecular geometries. Draw the Lewis structure. Use that Lewis structure to find out how many attachments you have. Attachments being lone pairs and bound atoms grouped together. This will get you down to the 5 basic geometries. If there are no lone pairs, then that will give you your answer. However, if there are lone pairs, then you must go and separate your lone pairs from your bound atoms to then figure out which advanced molecular geometry you're going to use. Let's try a few examples using the Vesper model to predict the geometry for the following molecules. So let us go ahead and start with our ASH3. So the nice part about it is our arsenic is in group 5, so we know that that is going to bring 5 valence electrons. Then each one of our hydrogens is going to bring 3. So right now I have used 6 of the 8 electrons in which I was given. So now I will go and put this pair of lone pair electrons on my arsenic. We can all agree that this has 4 attachments, meaning that this would have the tetrahedral electron pair arrangement. But this is not the tetrahedral molecular geometry because of that lone pair. So now, which molecular geometry do I have when I have the AB3E group? That is going to be the trigonal pyramid. So while I started with the tetrahedron, because of that lone pair, I now can answer this as the trigonal pyramid molecular geometry. So now let's go to our OF2. If I start with my Lewis structure, we are going to have the fluorines on the outside. We have our oxygen in the middle. I have a total of 20 valence electrons. So I will now put those in. The fluorines going first, and then finally I will go and put my lone pairs on my oxygen. Notice that I have the same tetrahedral electron pair arrangement because I have 4 attachments, 2 lone pairs and 2 bound atoms. But now what I'm going to have is the bent molecular geometry. The reason why is because I am having the 2 lone pairs on the oxygen. So this would be the bent molecular geometry. Let us go ahead to our aluminum tetrachloride ion. So now what I am going to have is my aluminum in the middle. I would have a chlorine, a third chlorine, and finally chlorine number 4 here at the bottom. Each one of these species is going to have their lone pairs. And because we have a charged species, please remember to put it in brackets. And we would go and place the charge there. So let's go ahead and look at our central aluminum. How many atoms do we have attached to the central atom? Well, notice that I have 4 atoms bound to my central atom, none of them being lone pairs. So this means that we have one of the basic molecular geometries. In this case, 4 attachments means that it is going to be tetrahedral. So we are going to have the tetrahedral molecular geometry. So let us go to D. Notice that I'm going to have iodine. So I have an iodine attached to an iodine. And finally, let's attach one more. So now I need to determine the total number of electrons. Well, if I get 7 from each one of the iodines, that's 21. With one more is 22. So let us go and start putting electrons here on the outside. Well, then the interesting part is that I actually have 3 lone pairs of electrons that I'm going to put around my central iodine. So this is going to be the AB2E3 group. So while it started as our trigonal bipyramidal electron pair arrangement, the molecular geometry in this case is going to be linear. This is due to the pairs of electrons on our central iodine. So finally, let's go to our last example, which is going to be our C2H4. So this means that we are going to have 2 carbons located in our molecule attached to each other, each one of them having a hydrogen. And if we do an electron count, we are currently electron deficient, but we have 2 more electrons, so this means that we can form a double bond in the middle. So let's see how this affects with having a double bond. If I look at my left carbon, you'll notice that I have 3 bound atoms. I have 2 hydrogens and 1 carbon. When we are trying to determine the electron pair arrangement, remember that we treat single bonds, double bonds, and triple bonds as just one attachment. So our left carbon, having 3 attachments with no lone pairs, is going to be trigonal planar. Remember that our trigonal planar molecular geometry has a bond angle of 120 degrees. So then let us go and look at the right carbon. Does it have the same molecular geometry? It does. Notice that our hydrogens are 2 attachments, and then our double bond that we already counted from the other direction is our 3rd attachment. So for both of our carbons in this example, we are going to have the trigonal planar molecular geometry. Remember that if you are given multiple central atoms, you need to tell me the geometry of all possible central atoms. The final example that we are going to do is look at the seesaw molecular geometry. So which of the following molecules has a seesaw molecular geometry? So the first thing that we need to do is go and look through all of our possibilities. So let us go ahead and start with answer A. We have xenon with 4 fluorines. So let us go ahead and attach 4 fluorines. If we start with 4 fluorines, that is going to be 28 valence electrons. Then with xenon giving us 8 more, that is going to be a total of 36 valence electrons. So if I do this and place all of our lone pairs on our fluorines being the most electronegative atoms, we end up with 2 extra lone pairs, and we can put those on the xenon that we see here. This is going to be the square planar molecular geometry. So this starts as octahedral by electron pair arrangement, but as you can see here would be square planar. So answer A is incorrect. Now let us go to our sulfur tetrafluoride. In this case, we are going to put our sulfur in the middle. We have our fluorines that we will attach. So in this case, we are going to have a total of 34 valence electrons. So let us go and put in our lone pairs on our fluorines. And finally, when we get to sulfur, notice that we have one pair of valence electrons that are lone pairs on the sulfur. So now this is going to be the AB4E group, which is the seesaw molecular geometry, and this would have that specific molecular geometry. So right now, answer B is a very good possible answer. Let us go ahead and look at our silicon tetrafluoride. So now what we can do is say we have our silicon, we have a fluorine, our third fluorine, and finally our last one. We would start with the 28 electrons from our fluorine. We get 4 from silicon. That is going to be a total of 32. And if I put in lone pairs for my fluorines, you will see that I am going to have used all 32 electrons, and I will end up with the tetrahedral molecular geometry. The nice part about this is that answer C actually gives us the ability to answer part D very easily. The only change between C and D is the central atom. The number of electrons is the same. So you don't have to go out and draw answer D to know that it is wrong, because this would have the same tetrahedral molecular geometry. Finally, let's go to E. Well, one of the biggest issues here is that the seesaw molecular geometry only has 4 bound atoms. So if we go and look at answer E, this cannot be the seesaw molecular geometry because we have 5 attachments. This is going to have a different molecular geometry, so E would be incorrect. In this video, you saw the importance of how lone pairs of electrons on our central atom are going to change our molecular geometries from very easy, basic 5 molecular geometries to now variations that are going to have different bond angles, different interactions due to our lone pairs, and are going to give us a variety in the shapes that we see. Have a great day.